The PS2 host controller contains a transmitter, but before I jump into the design and implementation of this transmitter, I just want to emphasize an idea here. So when we talked about the receiver system, we have dealt with the clock and the data inputs only, because the receiver system only listens to the bus, does not need to send anything, because the protocol doesn't tell it to send anything. However, when we're dealing with the transmitter, it's a little bit different in here. The PS2, the clock, and the data are bidirectional in here. And the reason why is because the protocol tells me if you want to send something to the device, basically the host wants to send something to the mouse or the keyboard, it needs to take control of the clock, set it to 0 for a short period of time to indicate to the device to stop so that it can actually listen. And then it switches and start listening again to the clock that is generating by the mouse of the clock. So this is bidirectional. The same goes with the data. When it's sending, it's actually sending that, but it also can receive the acknowledgement. So the way we'll be implementing this particular mechanism is the following. So the receiver itself, regardless of how we implement it, will have the following signals. So this is where the bus is, and we're going to deal with it as a bidirectional bidirectional signals for both of them using tri-state buffers. So the implementation in here will utilize a couple of signals, which is tri-C, which stands for tri-state buffer for the clock, and the tri-D, which is tri-state buffer for the data. So if this is asserted, for example, you have set this to exactly 1, what you're doing is you're effectively activating this buffer. So what this does is actually let the transmitter send a signal. We're going to call it PS2 out for now, and that signal will go to that bus. Generally speaking, for the PS2 clock, it's just going to be that 0 for a short period of time, indicating a request to send. Okay, but if you actually do not put a 1, you just put a 0 in here, that indicates that this particular buffer is not connected, so this signal is not connected. So what happens with the clock is none of these is connected, so the clock, technically speaking, just becomes an input to the transmitter. So the tri-state in here, whether it's the data or the C, is actually what's going to let us tell us whether the controller is taking control over the signal or actually just listening to that signal. So let's jump into the design of this particular transmitter. It's pretty similar to the receiver. It's just have a little bit more states in there. So it just follows the timing diagram on the protocol like we have done before, and here's the whole system. So let's see how it's doing. First, we know that it has an idle state, it has a request to send state, it has a start state, and it has a data state, and it has a stop state. So it has a little bit more states than the receiver. So let's see what's happening in idle. So in idle, it's actually telling me, okay, the transmitter is idle, so this particular signal is asserted, so the processor knows that it can send, and also the receiver knows that it can receive if it wanted to. And what it does in this particular state is actually the transmitter is just waiting for some signal we call a write PS2. And this signal is actually asserted usually by the processor because it wants to send something. So the processor, generally speaking, makes sure that the transmitter is idle, and then it actually asserts this. When it does assert it, it actually says, okay, that means I want to send something. What does it send? Well, actually it sends this byte, which is asserted in here. So this is basically our 8 or whatever the processor we're going to send a byte. We're going to do that in here. We're going to compute the parity, and we're just going to concatenate them and put them in a register we're going to call B. At the same time, we're going to call it, we're going to just load another register we're going to call C, and that will be just a counter to count for that short period of time that the clock is going to be to 0. It's actually this particular one in here. So the next state will have C as a counter loaded with 111, and we're just going to wait, as we'll see shortly. Okay, so the purpose of that C is just to keep track for this particular 0.1. Frankly speaking, this will not be 0.1 millisecond or 100 microsecond. This is a 13-bit, basically a bunch of ones. And if you compute it exactly, I believe that number, or the number, like the wait time that it will actually do, is exactly 81.92 microseconds, I believe. That's basically what it would, which is close enough to the 100 microseconds. Anyhow, before I jump into the rest of the system, I just want to make sure emphasize that when we're going to look at the implementation, there's another state in here that is inserted, and that state is actually not shown on this diagram, and that's why I'm not showing it on the finite state machine either. That state, its purpose is just to make sure that the RX is idle. So the state is going to be called wait till wait for Rx, basically, or wait R. That means wait till the Rx is idle. So in here, if you take a look at this finite state machine, it actually does not utilize this Rx idle because it's in that little hidden state. And the reason, again, is because that is not shown in here. Again, the purpose for this is just to make sure that the receiver is not receiving anything. You should not be sending in the middle of the receiver receiving a byte. So if the receiver is just basically on byte 5 out of 8 or whatever it is that it's receiving, just wait for it to finish. When it finishes, now you can actually send whatever you want it to send, and that's it. You take control of that bus. Anyway, we continue in here. So the request to send in here after we wait. So the idle, basically the processor asserted this, put whatever data it wants to send, and then it waited for the RX to make sure that it's actually done, and then it goes to request to send, and request to send is actually according to this. All it does, it makes sure that the host actually drags the clock to 0, and that's exactly what it's doing in here. So we see that the tri-state C basically is asserted now to 1, which tells me that the controller, the transmitter wants to take control of the clock, and it's just going to make it at 0 for a short period of time, and that's basically C-1, C-1, C-1. It's just going to keep doing this till all these 13 bits basically goes from 1111 13-bit ones all the way to 0, and that guarantees that particular period of time is actually happening. And at the very end of it, that's it. You're out of the request to send. You actually move to the start, and the start is just basically taking control, or the host will take control of the data line. And the way it's going to do it is by asserting the tri-state data, so that it wants to take control of the line. Anytime you see tri-data or the tri-state data, that means I'm controlling the data. For me is an output. I'm taking control over it. What does it do in the start? It actually just puts a 0, and it detects a falling edge. This falling edge detector is exactly the same as the one in the receiver. It actually just goes in here and makes sure that there's a negative edge in here. When it sees a negative edge, it's actually going to move to the next state, which is data. Okay, but before it does, I'm going to load n by 8 because I want to send 9 more bits. So what happens is like 0 to 8 is 9 more bits because I already sent the start bit in here because it was already in here. So all I have to do is like this 0, 1, 2, 3, 4, 5, 6, 7, and 8. It's actually the 9 bits. Okay, so we're going to do that. We go to the data, and in the data is, again, the tri-state data is 1 because data now for me is an output. Remember, the host is actually taking control of the data in here, so it's an output for it. And what it does is actually take that B that we loaded essentially with the data and the parity. It's just B0, and then when a falling edge comes in, we just do a shift. Basically, we get rid of that least significant bit, and we do a right shift, so the next time around is actually doing that. So basically we're doing a D0, D1, D2, D3 because we're shifting the least significant bit out one at a time, all the way till you actually transmit the parity. Once you transmit the parity, you actually go to the stop, and in the stop what you're doing is actually you're going to the default value of the tri-D, which is actually 0, which indicates that you want to release the data line. Okay, and you release that data line so that the device can take over and actually sends an acknowledge. So on the next active edge of the clock, we can read the acknowledge, but again, this particular design is not taking care or considering errors in the parity or the start bit or the stop bit. We're just basically doing the simple version of the transmitter. So once that negative edge happens, we can actually move and say, hey, okay, we're done. We can basically just issue a tick in here, and that particular tick will issue, we can read it towards here, but we're not using it in the whole system, but it's available for us if we wanted to, and then it goes to the idle state one more time. So now we jump into looking at the code and how it's all implemented. It's pretty straightforward. It's very similar to the receiver. So we take a look in here, we will see that it actually has that particular edge detector similar to the one in the receiver side, along with the filter, the 8-bit filter that we have in here, and then the finite state machine is very straightforward. Follow this diagram, except for this particular addition for the wait R. And if you take a look at the wait R, it's just basically making sure when the RX is idle, basically you can stay in that state till the RX idle, which is here, is asserted. Once it's asserted, now you can move to the RTS, and you can basically start the send procedure. And that's basically the only addition, or the only addition to the diagram, the only addition that does not show in the diagram. It's actually live in here. I should have just put it in here if I wanted to be more accurate. The other thing I want to show you is the following. We have the tri-state in here. It's based on the tri-C. So the tri-C, if it's asserted, we just basically output the output in here. If it's not, we just disconnect it. When you disconnect it, basically you release the data for the device or the bus for the device so that it can actually take control over it. Another thing I want to show you is actually here the parity bit. That little p in here, or par, it's actually computed using the dn. And because we have an odd parity bit, so the dn is the thing that the processor wants to send to the device. It's actually 8 bits. We take these are reduction operators. So one XOR, basically it's XORing all 8 bits, and then you're taking the NOT. So technically what we're doing is this is an XNOR or exclusive NOR. And that's how we compute the parity bit, and then you'll see at some point it's actually loaded along with the DN together in here.